before we can talk about probability, we have to first define these three ideas of experiment, sample space, and event. An experiment is an activity that produces an outcome. The sample space of an experiment is the set of all possible outcomes. And an event is a subset of the sample space. Okay, here's an example. So an experiment might be that on a certain weekend, we observe on each day of the weekend whether it rains. Okay, so that's the experiment. Does it rain on Saturday and does it rain on Sunday? That's what we observe. So the sample space here would be all possible outcomes. So one possible outcome is RR, meaning it rained on Saturday and it rained on Sunday as well. That's one possible outcome. Another possible outcome is that it rained on Saturday, but it did not rain on Sunday. Another possible outcome is that it did not rain on Saturday, but it did rain on Sunday. And finally, the last possible outcome is that it did not rain on both days. So these are our four outcomes. And if we put them together in a set, we have S, which is our sample space. It's the set of all possible outcomes of the experiment. Now, for this experiment, we don't care about the time of day that it rained. We don't care about how heavy the rain was. We don't care about how long the rain lasted for. We just care about, did it rain over the course of Saturday and Sunday? So that's a sample space. And then we can have various different events that could happen. So here are some different possible events that we can talk about. One possible event is that it rains over the weekend, sometime over the weekend. So remember that an event is a subset of the sample space. So we'll call this subset E1, and it's this subset. So it's all the elements of S except for the last one, because this means that it did not rain on both days, but this event E1 means that it rained sometime over the weekend. So that means it either rained on both days of the weekend, or it rained just on Saturday, not on Sunday, or it rained just on Sunday, not on Saturday. Okay, so that's again, this is an event. E1 is an event, and it is a subset of S. Here's another possible event. It rains on Sunday. Now, I don't say, this event doesn't specify whether or not it rained on Saturday. So it could have rained on Saturday, maybe it didn't. But all this event specifies is that it rained on Sunday. So this would be the subset of S, the following subset of S, where you have either rain on both days or just rain on Sunday. But these two things together are the elements of E2. And again, E2 is a subset of S. Here's another possible event. There is no rain at all over the weekend. Okay, so this is a subset of S that has only one element, where the N, right, does not rain on Saturday, does not rain on Sunday. And here's another possible event. It rains on just one day of the weekend. Right, only one day of the weekend. So we can call this event E4, and this is another subset of S, so either it's Rn or Nr. Okay, so now that we have these ideas, we can define probability, what probability is. So the probability of an event, so whenever we talk about probability, we're talking about the probability of an event, which again, remember, an event is a subset of the sample space. The sample space is all the possible outcomes. So the probability of an event E, which we denote like this, P of E, probability of E, this is the likelihood that the event will occur when the experiment is performed. Now, a probability, P of E, is always a real number between 0 and 1. So if it's 0, it means there is 0% chance of the event occurring. 1, if the probability of something is 1, it means there's a 100% chance that the event will occur. So, and then every probability is somewhere between 0 and 1. All right, so it could be 0, could be 1, but most often it is somewhere, not 0, not 1, but somewhere in the middle. So it could be any real number between 0 and 1. Now, we have a very handy formula, which we're going to be using throughout these videos. So, but it's very important to point out, before we even state the formula, it's very important to point out that this formula is only valid in a very specific situation. which happens to be common in many of the examples that we'll do, almost all the examples that we'll do. But it's important to keep in mind that we have to have this caveat in mind. So when dealing with an experiment in which all outcomes in the sample space S are equally likely to occur, okay, so that's this thing in bold here is the important part. In other words, this is a very important prerequisite. Before we can think of using the formula, we have to make sure that this is true. We have to make sure that all outcomes in the sample space are equally likely to occur. But if we have that, then the probability of an event E is this, the cardinality of E divided by the cardinality of S, meaning the number of elements in E and then divided by the number of elements in the sample space. Now, to help you remember this, this caveat, this prerequisite, because the formula itself is easy to remember, but in order to, to help it maybe click a little bit why this formula needs to have this caveat at the beginning. So it might help to think about buying a lottery ticket, right? You buy a lottery ticket, there are two possible outcomes. You win or you don't win, right? You win or you lose. The event I'm interested in is that I win, right? So that's my event, that I win. So you might say the probability that I win should be 1 divided by 2, because the event is that I win. The sample space is that I win or I don't win. So it should be 1 divided by 2. So there should be a 50% chance of winning a lottery. But the reason that's obviously not true is that this formula doesn't work there, right? This formula is totally inapplicable there, because the two outcomes, right, that I win or I don't win, are not equally likely to occur. They're very, very, very different. They have very, very different likelihoods. Okay, here's an example. On a certain weekend, we observe on each day of the weekend whether it rains. This is the same sample space that we talked about before. So here's our sample space. Assume that all outcomes in the sample space are equally likely to occur. Now, this is a huge assumption, which is really not justified in the vast majority of the world, right? You might say, well, well, maybe this and this are both equally likely to occur. Okay, that's fair enough. But is it equally likely that it will rain both days and that it will, as it will not rain both days? Whatever. In certain places, it is true. But let's assume for simplicity that each of these 4 outcomes are equally likely to occur. So we would like to know, what is the probability that it will rain over the weekend? Okay, so in other words, what we're really asking is, again, this is sort of not a very official way of writing it. I'm just writing it like, this is like pseudocode, right? But here's the real code. Probability of this event, and this is a subset of S. This is a subset of the sample space, and this subset represents the idea that it rains sometime over the weekend. Either it rains on both days, or it rains just on Saturday and not on Sunday, or it rains just on Sunday and not on Saturday. But this is the event, and we want to know what is the probability of this event. So since we're assuming that each outcome in S is equally likely to occur, we can use our handy formula. So this is the cardinality of the event, right, that I'm interested in. So the cardinality of the set divided by the cardinality of S, right, divided by the cardinality of the sample space, which is 3 divided by 4, or 0.75, or 75%. These are equivalent answers, right? 3/4, 0.75, 75% are all represent the same thing. Continuing with this example, what is the probability that it rains on just one day of the weekend? So this is asking for the probability of this event, right? The event that either it rains on Saturday but not Sunday, or it rains on Sunday but not Saturday. So what is this probability? Well, this would be the cardinality of the event divided by the cardinality of S, which is, well, really it's 2 divided by 4, which is 1/2, which is 0.5, which is 50%. Another example, suppose we have two dice, which are fair dice. If I don't specify otherwise, you can assume that they're fair dice, but here I just said it anyways. But you have two fair dice, one white one and one black. Okay, so the point is they're distinguishable from each other. So whatever. If you roll both of them, question is, what is the probability that at least one of them will be a 6, right? So when you roll a die, you either get 1, 2, 3, 4, 5, or 6 on the die. So here we're rolling 2. What's the probability that at least one of them will be a 6? Okay. So here is our sample space, right? Because when we roll a die twice, when we roll two die, rather, when we roll two die, one white and one black, here's well, we can get 6 different possibilities for the white die, right? So either we get a 1 for the white die, or a 2 for the white die, or a 3 for the white die, or a 4 for the white die, or a 5 for the white die, or a 6 for the white die. And then for each of those options for the white die, we have 6 different options for the black die, right? So this first row is all where the white die has 1, but there are 6 different options for the black die. And then the second row here is all the cases where the white die is 2, and then we have 6 different options for the black die. So altogether, we have 36 different possible outcomes of rolling two dice. All right, so this is our sample space. It's our sample space. And now we want to figure out the probability that at least one of them will be a 6. So let's try to figure out what the event is, right? What is the event in terms of the sample space? Which part of the sample space is the event that we're interested in? Right, so, well, if you think about it, it will be the top row. I'm sorry, I misspoke. I think I used the word row before when I meant to say column. Anyways, and this first column is all the cases where the white die is 1. The second column is all the cases where the white die is 2, and so on. Okay, so again, we're looking for the ones where at least one of them is a 6. At least one of the two dice is a 6. So we see here that the top row has all the possible cases where the black die is 6, and also the right column has all the possible cases where the white die is 6. Right now, we also include this corner here where both of them are 6, because that's still in the event that we're looking for. We're looking for at least one of them being a 6, but that includes the possibility that both of them are 6s. Okay, so here we have our event E, right? So event E is a subset of S, and we would like to know what is the probability of this event. So it's pretty straightforward now. The probability that at least one die is a 6 is equal to probability of E is, now since all of these events are equally likely because these are fair dice, right? So each of these events is equally likely to happen, so we can just use our handy formula. This is the cardinality of E divided by cardinality of S, which is 11 divided by 36. All right, if we count the elements of E and then we count all the elements of S, we have 11 divided by 36. Great. Next example. Suppose you deal a 5-card hand from a shuffled standard deck of cards. Okay, so we have a standard deck of cards. We've seen this before, 52 cards. And we deal, meaning we take out 5 cards, a 5-card hand. And remember, a 5-card hand means a group of 5 cards. And in a group, the order doesn't matter. Okay, so in a hand, the order doesn't matter. It's not a lineup where I care about the order, but it's just a group. It's just a hand of cards where I don't care about the order. Now, what is the probability that all 5 cards are of the same suit? So remember that a deck of cards has 4 suits. Those are hearts, diamonds, clubs, and spades. And what's the probability that all 5 cards are of the same suit? Meaning, what's the probability that either all 5 cards are hearts, or all 5 cards are diamonds, or all 5 cards are clubs, or all 5 cards are spades. So here we have to start with the sample space. So the sample space is, let S be the set of all possible 5-card hands taken from a standard deck. S is our sample space, and each outcome in S is equally likely because it's a shuffle deck, right? And it's a standard deck, so I don't have to worry about, like, there being extra cards of a certain type. Everything's equally likely here. So that's S. That's our sample space. Again, all possible groups of 5 cards taken from a standard deck. Now we can ask, what is the cardinality of S? Because we're going to need to use this. So what is the cardinality of S? Well, we have 52 cards, and we need to choose 5 of them. We don't care about the order. So that's 52 choose 5. That's the number of ways that we can take a 5-card hand from a deck of 52 cards. Okay, but this is, again, all possible 5-card hands, not caring about whether they're of the same suit or not. Now we're going to define our event. Let E, which is a subset of S, be the set of all possible 5-card hands that are of the same suit taken from a standard deck. Now we have to ask, what is the cardinality of E? So to count the elements of E, we will divide them into 4 non-overlapping categories. So the first category is where all 5 cards are hearts. Right? So again, this is a category, meaning we have lots of different options in this category, but the common denominator of this category is that all 5 are hearts. Now there's, you might have lots of different possible groups of 5 cards, even where all of them are hearts. Even with this restriction of all 5 being hearts, you still have many different possibilities. That's one category. Second category is that where all 5 are diamonds. Third category is where all 5 are clubs, and the fourth category is where all 5 are spades. Now these are non-overlapping categories because if all 5 are hearts, then it's not possible for them to be all diamonds and so on, right? So these are non-overlapping categories. So now what is the cardinality of E? So we just need to count the size of each of these categories and add them up. So cardinality of E, well, what is the size of the first category, for example? What is the size of the first category? So again, I'm looking for 5-card hands where all 5 are hearts. So in a standard deck of cards, we start off with 13 hearts, and we want to choose 5 of them to be part of our hand. So that's 13 choose 5. And that's the same thing for all of these 4 categories. So the cardinality of E is just going to be 13 choose 5, that's for the first category, plus 13 choose 5 for the second category, plus 13 choose 5, that's for the third category, plus 13 choose 5, that's for the fourth category. Okay, so that's the cardinality of E. So now it's easy to find the probability of the event. So probability of E, meaning the probability that when I take these 5 cards from the deck, that all 5 cards will be of the same suit, this probability is equal to the cardinality of E divided by the cardinality of S, which is 4 times 13 choose 5, right? It's just, 4 times that, because, right, in other words, instead of adding them up 4 times, I could just do 4 times 13 choose 5, divided by 52 choose 5, which comes out to be this, which is approximately 2 out of 1,000, right? So approximately 2 out of every 1,000 times that you take a group of 5 cards from a deck, approximately 2 out of every 1,000 times, you'll see that all 5 cards are of the same suit. So pretty unlikely,